Hello, Virginia. Good morning, good afternoon, good evening, dear friends of DigitalFUTURES. This is Philip Yuan from Shanghai. Welcome to our weekly talk session. Tonight, very special. We have 5 special guests all from China, some very representative young researchers and practitioners. So the topic today is, the theme of tonight is recessive structures. DigitalFUTURES events, as you all know, is a global academic sharing platform in post-pandemic era. So recently, we have been focused on the new technology development in the process of digital evolution, locality, and culture. Advanced researchers and studies from young researchers, as well as some prominent architects and professors across the world, participating in this special platform. I think if you remember, just 2 or 3 weeks ago, we invited 3 prominent professors from UK and Europe, including Professor Chris Williams, Professor Segrit from Princeton, and Professor Philip Brock from ETH. All of them gave us insight of shell structures. Tonight, I think we would like to keep on the topic on structure. The theme would be the regressive structures. As we know, digital technology has cultivated an integrated model of design process that has sought to reconnect architecture and structure engineering. What unique approaches towards integration are being cultivated in China, given its long history of archi-engineering? This is very interesting. We invited different background researchers and architects, structure engineer coming here to talk, have their different background, different perspective to analyze their understanding on the structure in architecture. Before we move into the presentation, please allow me to briefly introduce our guest tonight. So the first speaker tonight would be Yuan. Dr. Yuan is an architecture historian. He is a member of KUST Gesellschaft. He has received his PhD on the building archaeology at Technical University of Munich, Germany. He is the author of the book Woven Arch Bridge, Histories of Constructional Thoughts. That is a very important book of him. I think probably he will introduce the content and his research in the past 20 years. And he works now as a lecturer in Kunming University of Science and Technology. His presentation topic today is, why do we study woven arch bridges? I think I would like to introduce one by one. And first, Yuan, would you like to share on your screen, firstly? So I think it's a really long day for Yuan because yeah, he experienced a fantastic seminar in Hong Kong online.
Thank you, Professor Yuan, and thank you, everybody. Good morning, good afternoon, and good evening. So I'm really glad that I have the opportunity to share my studies and some of my thoughts with you, and especially under this topic. To tell the truth, I'm a little bit hesitant to join the discussion today. So when Professor Yuan invited me at the very beginning, I was really hesitant. The topic today is not really my field. I am an architectural historian. In the past 10 years, I dedicate myself into the study on a special kind of historical structure, woven arch bridge, and has my study published last year. So woven arch is a modern term describing an arch-shaped structure which is composed of interlacing timber. The longitudinal and transverse logs are organized in a form like the web and the weft of textile. Thus comes the term woven arch, taking the folk game, chopstick game, as an extreme representative. A woven arch structure could achieve a scale larger than the beam or cantilever structure. Such a bridge could reach a clear span to some 40 meters before modern times. In East Asia, this means it is the largest span capability for timber structure before modern times. In Southeast China, more specifically in the mountains between Zhejiang and Fujian provinces, a group of circa 100 historical woven arch bridges have preserved until today. They are featured by the woven arch and the dark structure. The craftsmanship building such a bridge in Southeast China has been enlisted as a UNESCO intangible cultural heritage. And this kind of structure is classified under a larger scope of structure type today, the so-called reciprocal frame structure in modern sense. And it is a somewhat popular structure type in the modern design. Many architects, architectural institutes have engaged in the developing its design method of this type of structure. An early pioneer was the Japanese architect Kazuhiro Ishii in 1990s. Based on the design work of Ishii, Professor Ola Popovik Lassen from Denmark established the term in the academic field with her book, Reciprocal Frame Architecture. Professor Vito Bertin from the Chinese University of Hong Kong discussed composition principles of this structure type and made it known to many architectural schools in mainland China via experimental workshops. Another important research group is the team of Professor Anita Spiro's team from ETH Zurich. They developed the digital design system for the rather complicated structure and published in Dr. Udo Tunisen's book, Traditional and Innovation Reciprocal Frameworks. Even the Pritzker Prize winner Wang Shu has been famous for his construction experiments with the woven arch and reciprocal frame structure. And today, many architectural schools has taken this structural form into their training system, including Nanjing University, where I took part in the teaching. So if anybody who wish to get some inspiration on the design from the historical structure, the above mentioned books and scholars are good reference. But modern utilization was never my aim. As a historian, what we care is the operating principle of the historical society and the historical context, which is, in most cases, fundamentally different from our time. In other words, we look back to the past, not towards the future. So when I was invited by Professor Yuan to this symposium, I'm very grateful for this trust and encouragement, but I'm really have great angst to join such a topic facing the future. So finally, I cite my topic of the talk. Why do we study woven arch bridge? It's actually the question to myself. Why do I study the woven arch bridge? From the viewpoint of an architectural historian. So I'd like to share some of my personal understanding and answers to this question from at least one aspect from a higher level. So how did I engage myself into the study of woven arch bridge? At the very beginning, it was a personal practical choice. I studied civil engineer for my undergraduate education and turned on to architectural history from my master's phase. This road led me onto the way of technical history, hoping that my training on structural science might be benefit to my understanding on the historical structures. However, the benefit never come in the way I'd expected. In many aspects, woven arch structure is a less favorable structural form in the sense of structural engineering. In material, inside a woven arch structure, most of the structural members are under great bending force. We know that timber works good under tension or pressure. While bending, bearing tension at one side and pressure on the other side inside the beam, is less efficient on utilization of timber material, where the middle section of the beam is a waste of material. Therefore, also considered as a large span structure, the structural efficiency of woven arch is far less than a common truss structure. in which members are intendedly designed either under tension or under pressure to achieve a best mechanic effect. Related to the interior force, the structural feature of woven arch is rather complicated to a mind trained with modern sense. The clearness in force state is one of the design rules in modern engineering. A truss is the best representative on this. The two force members in the truss not only explore the best loading capability, but more importantly, the clearness in structural logic enables comprehensive structure analysis. In this way, the truss is almost a symbol of structural mechanics. And the truss theory developed in the 18th century was one of the base stone of structural science since early modern times, and embodied some of the greatest building achievements at the time in the human history. The woven arch structure, on the contrary, is a representative of structural ambiguity. Firstly, its reciprocal feature means that all the members are tangled with each other. The little change on one member will result in an interchange in the entire system and onto itself accordingly. This makes great difficulty in the analysis and calculation. And the structural form is a combination of many features contrary to our common knowledge on common structure forms. For example, it works as an arch, but bears great bending force inside. Well, normally there shouldn't be bending force inside an arch. And the arch needs thrust from abutments to keep it stable. But a woven arch does not rely on it. And in extreme examples like the chopstick game, the thrust will cause collapse of the woven arch. Its structural stability is actually relied on the load upon it. The greater the load, the more stable the structure until it reaches its load-bearing limit of the structure. So relatedly, the reciprocal mechanic means that every member is related to the entire system, and the failure of one member will result in the collapse of the entire system. This is exact opposite to the structural design principle in which safety plays a crucial role. The construction is another problem. Since all the members are reciprocal, supporting each other, the entire structure is unstable until the last piece of member is ready in place. And since all the beams are interlocked, the supporting system must be skillfully arranged to avoid hindering each other. Thus, a woven arch structure requires a well-designed scaffolding system, a well-organized construction process. Both of them are of great difficulty. Not to mention that complicated form is a difficult in design itself. All these unusual features aided in challenge and attraction to a modern researcher. This is why it is so popular today to architects and engineers. But all these challenges and difficulties also be the obstacles in a pre-modern world when there was no advanced calculation and analysis tools. So considering all these disadvantages of woven arch structure, how did they came into being in the history? Well, in every possible means along many different roads, woven arch bridge appeared in so many cultures and played in different times and places. They appeared in so many cultures and places in different times along the human history. In Renaissance Italy, in Da Vinci's design. In Qingming Shanghe Tu, in northern China plan in the Song dynasty, 11th century. In the 19th century in Japan, in the US, in Norway, in Germany, in Southwest China, Northwest China, and Southeast China. So most of these examples appeared singularly in their own region and culture, believed by the locals to be unique or even one of its type in the history. But when we dig out all these examples from all over the world, the isolation situation of these respective cases would reveal themselves meaningful information. There were speculations from both the East and the West, since the structural form is rather unusual. that the historical cases of woven arch bridges, especially the most famous Da Vinci design and the Chinese examples, were related by cultural influence and/or technique spread. However, according to my in-depth case studies, there's no direct connections between these cases. Just to the opposite, several of them, especially the Da Vinci design and the Chinese cases, they have almost the solid evidence to prove them with their own local technical origins. Let's explain it very briefly. So the Da Vinci's design. Da Vinci's story starts from his own cultural root, from Julius Caesar in the Roman times. Julius Caesar described a rather peculiar bridge design in his Gallic War, his own book, with detailed technical descriptions. He mentioned a bridge with it he was able to lead his army across the Rhine bridge. And in his technical description, he mentioned some special constructions which inspired many Renaissance Italian architects to study and reconstruct, including Arbodi and Palladio and Da Vinci. It was at a time when Italy was going through endless wars towards its neighbors, and both Palladio and Da Vinci hold their aim to study the military technique from their Roman ancestors to help their soldiers on the battlefield. Both of them have got the same inspiration from Caesar on a special wooden joint to interlock each other to enhance the stability of the joint. Da Vinci developed this idea to the woven arch bridge, and he named it articulately to weave a bridge. From this idea to weave an arch, he went further to the idea to weave a vault, thus inspires modern reciprocal frame structure we mentioned at the very beginning. Weave or textile is Da Vinci's archetype of design, and Caesar's bridge construction is his inspiration. There's other examples follow some other roads. The Norwegian examples take the local three-sided arch as an archetype, developed the woven arch by enhancing the joint of the three-sided arch. In some other cases, including the Japanese examples, and the two types of bridges in Southwest China and Northwest China, cantilever bridge plays the role of archetype for the development of the woven arch structure. But for the famous Qingming Shanghe Tu, it's another story. Here, outside the capital city Bianliang at the time, the so-called Rainbow Bridge was built to solve the traffic problem over the Grand Canal. The officers and craftsmen was facing the problem to build such a flying bridge without blocking the canal and the ship traffic. The challenge was more about the construction rather than the structural form. Their structure so much similar to the chopstick games that we have reason to believe that the game itself might have played the role as the archetype of the design directly. There are some other cases might be inspired by the similar playful game, including the Japanese examples of the different time and different places, and the German example. However, the most splendid examples are the group in the mountains of Southeast China. If all the others are either small-scale items or short-lived experimentals, the woven arch bridge in Southeast China are real construction projects to meet the basic living requirements of the local society, to fly over cliffs and deep water, to form a craftsman tradition for over 4 centuries. At the least developed mountain area, carpenters have figured out a set of design methods using rather primitive tools, drawings, and the calculation method, building the grand construction over the most dangerous site with the simplest scaffolding system. They have to develop an entire system of technique from the selection of joints to the cooperation of the carpenters with somehow acrobatic practices, to some secret meanings and measures to enhance the structure, many of which is out of the imagination of a modern engineer. All these examples, although rather similar in structural form, they are facing entirely different functions and aims, site conditions, historical environments. Their inspirations or prototypes of structure ideas could be totally different, and so do the technical strategy and construction processes. In a word, except the similarity in form of the mechanics principle, these structures are entirely different in every aspect. Woven arch structures have appeared in many cultures and times in the human history. Despite the strong similarity, they do not have necessary relations in between. The idea of woven arch mechanics, namely to weave an arch-shaped structure with straight timber members to achieve a certain span, could origin independently in any time at any place, as a coincidence in the similarity of form, with no necessary to be influenced by each other. Therefore, woven arch bridges appeared in history as a rather special phenomenon. It's unique yet universal. It appears as a rather unusual structural invention in place, isolated in its own cultural environments, but appeared isolated in so many different places and times. On the other hand, despite of its universality, it has also strong Chinese characteristics and regional features. Where among all these examples, most of them only appear shortly in the history, but only in China, more exactly only in the Southeast China, that woven arch bridge has developed beyond the scope of an accidental invention into a major and systematic technique, and has developed a several century-long craftsman tradition. So here comes the significance of the study on the historical woven arch bridges. It offers a special angle of view to observe technical history of human being. By asking the question, how were the cases coming to being in their own culture and historic context, and how did they develop in one and vanish in another, they could get a deeper understanding of all these peoples and building cultures, especially the one of our own. Seen from this sense, the study on the craftsmanship of woven arch bridge in China reaches far beyond the preservation of an out-of-date technique. It's a key to understand our building culture and many other cultures. For example, in my study, I have to face the question, why that the most developed and inheritable technique of woven arch bridge only appears in China? This question is actually highly related to another one. Why that truss structure never developed in Chinese tradition? These two questions are actually the two sides of the same coin. It is understandable in the European cultures where truss has a long root in their building history, and with the fact that truss is a much more effective structure form in span capability and in construction convenience. There's no urgent need for people to explore the possibility of woven arch structure, even when they had come out with the structure idea. On the contrary, in China, where truss was never a structural option at hand, facing the challenge of span, when the idea of woven arch came into being, it's more likely that it might take a chance to take the root in the building culture. Therefore, my question of woven arch versus truss could be understood as a sub-question of the famous Needham's question. He asked, why did modern science take its materialistic rise in the West at the time of the Galilee, and why it had not developed in Chinese civilization? So seen from this aspect, the comparison between the woven arch and the truss is actually a comparison between the Eastern and Western building cultures. We mentioned above rather briefly that woven arch in some aspects, including some mechanical features and structural logic, is exactly opposite to the truss structure. Their differences exist in mechanics and constructions, but also in the representative to their, but also as a representative to their culture, to their cultures. So therefore, the study on woven arch bridge From one hand, it's a key to understand our building cultures, especially on comparison with the Western civilization. From the other hand, the study on this less efficient structure, judging from the system of scientific study, provided us with some building strategies from other systems. The logic of understanding the structure, the means and the process of construction outside the routine provided by a scientific approach. The human history has provided with us with the colorful artworks and the possibility of construction. So this is my share. Thank you.
Fantastic lecture. I think it gave us a profound address of this kind of timber structure. Cross timber structure goes into not only the history, but also different regions around the world. I think we can make further discussion afterwards. Let me think about the questions. Goes to Liu Yan. And then let's secondly invited the speaker, Zhang, to give us a special presentation. So Zhang is a very special structure engineer, and he has got very successful, right now it's like a booming star in the architecture field, because a lot of small office right now in China, they want to invite Zhang to be a partner, design with them in different projects. He is actually working, legally working in Tongji Design Institute. At the same time, he has his own office named A&D. And he is the co-founder and the chief structural engineer of A&D office, who has extensive collaboration with famous architecture firms globally. And he completed a number of well-known projects successfully in China. And I think including the Long Museum on the West Bund, Shanghai, and including the Light of Internet Expo Center in Wuzhen, who collaborated with my office. And also he gave a prominent research in different scenarios of the structure implementation in architecture. So today, Zhang will give us a presentation on topic of structure woven by clues, also as kind of woven structure. Please, Zhang, would you like to share your screen right now?
Okay. Thank you, Professor Yuan. And hello, everyone. It's glad to join this sharing. I'm a structural engineer, and my lecture topic is structure woven by clues. At the very beginning, I want to talk some personal view of structure. One kind of the structure is the law of the nature. For example, the mathematical fractal structure and turbulence of mixing liquid and vibration pattern of different frequency. All of this is objective. We can't change these rules, but we can use them. And the other type of structure controlled by our mind. For example, the painting composition, the music melody, and the form of capture. These are the reflection of our mind. Although these structures are subjective, but they are also under some laws of beauty. And the last type is the evolution structure. All living things, including ourselves, are this type. In the process of adapt to the environment, the structure constantly evolves. Although the evolution need obey the natural laws, but our mind also can influence this process. And in this process, the subjective and the objective can mix. So in this view, anything is structured, or structure can be a way of looking at this world. I think this attitude can affect our structure design. Next, I want to share two projects designed by Professor Philip Yuan and me. The first one is a conference center in Zhun, China. In the left picture is the landscape of Zhun. This is a typical view of water town in southern China. You can see the continual gray tile roof and white walls. So the continual roof became the design concept of this project. And in the right picture, it shows the original mode of the design. This building is about 90 by 200 meters. And the design and the construction need to be finished in 7 months. So that's a great challenge. In our design, we have to deal with it. Another challenge comes from the protection requirement of the water tower. The new building's room must be tile or something like tile. Obviously, the light white steel structure roof is a common choice for large space building. The real tile is too heavy for that. Of course, using metal tile is an option, but we want to make the white of the real tile to be a favorable condition through the structure design. So we consider the suspension roof. These three projects has certain reference value for us. The Pentrigase National Pavilion in Expo 1908 has a real concrete roof. It's very thin, but heavy enough to resist the wind. And Expo Hall 809, it's a multi-span suspension roof. And the roof spans are equal length. And the Eugene National Stadium, it has an irregular overhanging steel roof. It's heavy enough too, and reach suspension by flexible cables. What we need to do is to develop their ideas. And the most important thing is to use the real tile as the wind resist counterweight. Our project has 5 different spans in long direction. The height of ridges are also different. This roof is like a clothes hanging on the roofs. We fix the both ends by oblique columns and ground anchor cables. The middle supports are elastic, so this is a semi-rigid suspension roof. In this picture, it shows the oblique columns and anchors. The columns are hidden in the curtain wall. You also can see the height of the ridges are different. At the ridge, we use a beam string to support the suspension roof on both sides. It is necessary to carefully adjust the span and the sag of the suspension beams. This can avoid torsion on the beam string caused by unbalanced force. The unbalanced force comes from the suspension beams. On the other hand, reduce the span of the beam strings is also an effective measure to optimize. Now the main structure system is finished. The right part is the beam string and the A-shape support of them. In the A-shape is the equipment space. And the blue one is the continuous suspension beam. The suspension beam is highly efficient and economical. So the 200 millimeter H-shaped section can span 48 meters. In the process of improving this system, we found that the mechanical performance of the arc beam is very close to that of the catenary beam. So we try to unify all suspension beam into same curvature arc. This can speed up the construction. At this time, I think I finished my job, but it's not really, because the owner changed his mind. At the very beginning, he wanted a whole unit space, but now he thought 4 divided space is better. To me, different space means a different structure system. If there are 4 spaces, I can use more columns to reduce the span, as you see in the right picture. After comparison, we found that although the original system has a large span, it has similar material cost, easier to build, and better space quality. And at that time, the foundation is preparing to build. So we keep the original system, but we don't want to passively respond to the space change. Although the tiles weight is enough to resist the wind, we add anti-wind cable at the location of space division. This cable is also the skeleton of the inter-curtain wall. We start this design at March 2018, and you can see the A-shaped supports had been installed at May, and all suspension beams followed. It started to install beam screen and oblique columns. In the left picture is the resist cable of the A-shaped supports. Suspension beam almost finished in June. In the left, the worker installed the link members, and in the right, they are laying roof panel and insulation. The suspension, the distance between suspension beam is 2 meters. It's just the economy span of the roof panel. So the pillars are no longer required. In the left, the beam string finished and the suspension beam just like a silk scarf lay on them. On the right, the curtain wall starting to install at July. For fast building, the tails per installed in the factory, as shown on the left, and in the right is the internal curtain wall. You can see the aluminum panel fixed on the wind resist cable. In this project, the beam screen is an important structure to show, and is also a skylight. You can see the suspension beams and the wind resist cable directly, but they seems like decoration. But in fact, they are also main structure. The A-shaped supports indirect show to us. Through the reasonable design of the structure, the tails change from negative to positive for a large span roof, and the detail of the design evolved with external conditions. The next project to share is a timber roof. It's located in Shanghai. There are 2 roofs cover the triangle courtyard. Because they use the same structure system, so I talk about the bigger one. It's about 40 by 60 meters, and it's independent of the houses on both sides. The roof is an irregular shallow shell support on 20 columns. Like the project shared before, this one also need to be built fast. It's about 4 to 5 months give to us. The good news to me is the roof can be covered by a polycarbonate panel that is lightweight. And the courtyard no need to close. So the horizontal wind load is small. For shell structure, the foam funding is necessary if treat the columns at the support condition. The shell form will be like the left. The other hand is form funding with the triangle edges as the support, like the right. Although the thrust of the left shell is smaller, but the curvature of the right is relatively constant and is easier to build, so we choose it. The rise of this shell is about 3 meters. Compared to a normal shell, it's shallow. The shallow shell need to resist axial pressure and bending moment, especially for this special shaped timber shell. After its creep, the addition bending moment will be obvious. There are many ways to resist the thrust of the shell. For example, the parallel cables or the triangle columns. But after researching, we choose another way, a composite system. You can see in this system, the middle part is a timber shell, and the edge is steel truss to transmit and resist the thrust. The balance bar at each corner holds the truss. In this system, the steel column doesn't resist the thrust, but they drift in earthquake or wind. It's an ambiguous expression of this structure. The fourth floor is not directly shown off. That's what we want. In this picture, you can see all steel parts, the columns and the edge truss. Next is how to detail the timber shell. As we know, the fourth floor through the shortest path. The arrangement on the left make it easier to transfer to the columns. But you can see from the entrance perspective, there are too many components. Consider the effect which was the scheme on the right. In this system, the fourth path become longer. So we want to use full-length timber member, and that can have a better stiffness. But the time and the cost of curved timbers can't be acceptable. We need another way out. So how to build a large span roof by short straight members? We reference the laminar roof. But in our project, it's a shallow shell. The joint needs better stiffness. So we must improve this original design. The goal of the improvement is to control the amount of the timber and better adjustment for installation on site and increase the bending stiffness of the joint. At the joint position, the timber member in one direction are through. In other direction, the bending member transmitted by 2 steel screws and connectors. 2 50mm timbers grip the steel connector and connected by self-tipping nails. After adjusting on site, the nails drive in. By using this joint, the roof can be built safe and quickly, just like building blocks. The stability of the shell and the connection between the shell and the truss are critical. So in the final design, the related components reinforced. In this way, the structure was completed on time, and the effect is good. In these two projects, structure design not only pay attention to stress, construction, and cost, but also many indirect design clues. This connection of clues reminded me of a Chinese classical. Thinking harmony with differences. This sentence comes from Confucius. I think our design faced the same thing. A design concept is important at the beginning, but there are so many changes by different reasons we need to face. Of course, keep the original concept is important, but the change itself make the design concept different. If we look at the world in a structured way, everything can be the clues of the structure. I think that's very important to structure design. That's all for today. Thank you.
Thank you so much. The fantastic lecture from Zhang. So thanks a lot for your present two projects we collaborate in the past 3 years. I think it's given me a very strong memory for the whole process, how my office working with you in the whole process. I think it's interestingly from architects, for example, the Zhun project probably is like we put forward the cable suspending system, but goes to actually the rigid steel structure suspending system. And then the second project we mentioned put forward like the timber, totally the pure timber structure, reciprocal roof system, but finally goes to the steel timber composite reciprocal structure system. So I think we want to put forward the question right now to make further discussion with you on how the structure engineer can give I think this kind of harmony solution, like quite a Buddha style solution. It's not like in the Western, a lot of structure engineer, they purely make some solution by some very pure solution and totally based on some very logical process. But I think it's more like you're more like a architects more, rather than a structure engineer, because it can make a lot of very interesting solution in the process of collaboration. I think it's a fantastic thing for architects. It's very lucky for my office working with you in the past few years. So we still have some very challenging projects going on. We're looking forward for the future projects coming out. So thirdly, we invited another speaker who is very successful in China and very special. I first met him not in China, but in MIT in Boston in the IASS conference. He actually moderated a special session on the ice structure in ISS. So whose name is Peng, and Peng is currently who is exclusive director of Sports Architecture Engineering Research Center at Harbin Institute of Technology, exclusive director of International Snow and Ice Architecture Innovation Research Center, and also who is a PhD advisor. He's also a recipient of Young Architects Award from the Architect Society of China. His main research interests, including the collaborative innovation of long-span buildings and structures, the climate adaptation design of buildings in cold regions, and design and construction technology innovation of ice and snow buildings. I think that's the most special part for him. And Luo Peng has led the IT team design and build a number of innovative ice shell works by applying the digital design methods, innovative construction technology, and creative ones of the best in the field of ice and snow architecture internationally. He will present the title today of his presentation is Innovative Practice of Ice and Snow Architecture based on the synergy of architecture and structure. So let's welcome Luo Peng to share his screen, please.
Okay, can you see me? See the screen?
Please.
Okay. Okay. I'd like to thank Professor Yuan for inviting me to take part in the Digital Future activities. It's my honor to report my team's work of ice and architecture and structure in recent years. There is a large area of cold region on the Earth. According to the data, more than 600 million people in the world live in the cold region with average temperature lower than 0 degrees in January. Long time for winter, low temperature, lack of sunshine, cold wind, and snowfall are the outstanding characteristics of cold region. Under the action of spatial environmental, unique natural landscape and have been formed. The material, shape, color, and the texture by adapting to the natural environment form the unique beauty of cold region. In the process of construction in the cold region, human beings have formed unique architectural wisdom. Ice and snow architecture is typical example. For example, igloo. The Inuit who live in the Arctic was the first to use ice and snow materials to build temporary houses. This kind of snow domes is named igloo. In winter, the inner room is up to 0 degrees. This is Kamakura in Japan. Kamakura is also was built by digging the snow out of the natural snow pile to form usable space. It's usually small in size and used for food storage and wine making. Later, it becomes a space for traditional Japanese festivals. The world's first ice hotel was built in Sweden in 1990. After that, similar ice and snow hotels, church, bars, and other ice and snow buildings has been built in Canada, Finland, Norway, Switzerland, and other places. Another branch of ice and snow architecture is ice and snow landscape buildings. In Harbin, my hometown, Harbin Ice and Snow World was built every winter since 1999. At present, it has become the largest outdoor ice and snow park in the world. The highest building reaches 60 meters. Since 2016, the international innovative design and construction activities of ice and snow architecture has been held in Harbin every winter. We work with many well-known institutions. They include IASS Group 21, Union of Arctic Universities, TUE, Cambridge University, Ghent University, Leuven University, Kent State University from US, University of Lapland, Tsinghua University, and so on. Through the cooperation of architecture and structure, we export the innovation of ice and snow architecture, structure, and the construction technology. This is the project made by not only by us team, but also by the teams from the university. In December 2016, in the campus of School of Architecture of HIT, the first ice shell building in China was designed and built by Chinese and foreign teachers and students. We called it Ice Lotus. The span is 11 meters and the height is 4.4 meters. The same year, a small model of the cloud tower, the other name is Flamingo Tower, was built to extermination. The workshop is part of the Ice and Snow Festival of HIT. For the students, the activity is not only a process of practice and learning, but also a happy festival. This is a picture of removing the mold from the ice shell. This is the picture when the project is finished. Combine the project, we tested the structure performance, thickness change, deformation, sublimation, internal environment of ice and of ice shell, and the influence of solar radiation. There are the results of the test. And the material test made by the team of Professor Wu Yue of School of Civil Engineering of HIT. Based on the above construction practice and the tests, from December 2017 and January 2018, the design and the construction of a cloud winter was finished by teachers and students from HIT and the TUE in Harbin. The height of the ice 541 meters, creating a new world record for the height of the ice shell. The project, for the project, we will cooperate with Professor Arnold Planck from TUE, Professor Wu Yue from HIT. This is the construction process of the tower. This is the effect of external, internal, and night view of the tower. This is the effect of the ice shell material and the texture. Just like the tower is made by cloud, the texture is not only made by human being, but also by the nature. This is the internal structure and the construction texture of the ice shell. In December 2018, we designed and built the ice shell bar and hotel in Harbin Ice and Snow World. The total building area is more than 600 square meters. The largest span is 22 meters. The project is first ice shell building put into practical use in China. During the design, construction, and maintenance of the project, digital model and the computer tools play the role to connecting each stage and realizing the collaborative design of architecture and the structure. Because of the time, I only show some pictures of the project. Yeah, this is a picture when the shell after mold removed and cutting. This is the picture after it finished. The picture from the lake and the indoor effect. In 2019, we used the air rims as the mold to find the form of the ice shell. So form finding and the construction of ice shell by air rims is helpful for mold control and cross construction for different types of work in the process of construction, and is also helpful for the innovation of architectural form. With the project, the combination of design, construction, operation, and the maintenance of ice shell based on multiple multi-objective optimization and realized. The site is same as last year. There are ice bar and ice restaurant in the site. The total building area is about 930 square meters. The building area of the restaurant is about 660 square meters. It's a hot pot restaurant. The project is based on the materials environment and the unique requirement of the architectural art. Comprehensive consideration of the need of the construction and the user by analyzing the influence factors of design. 4 key design elements are summarized. They are structure, function, construction, and art. The work starts from the design elements based on the digital design logical, especially a spatial digital integrated design system, and then integrated the digital design tool, building the technical route. Based on the site, structure, function, and art, the scheme of the building is formed and determine the digital model. The model is used for the performance simulation and optimization. The grasshopper based on Rhino is used for build the digital information model. In terms of structure, Cramba 3D is used for structural performance analysis. Scheme comparison and optimization. Consider the influence of solar radiation on ice structure is significant. Use ladybug for solar radiation analysis. Determine building form and orientation. In function, Rhino visual interface is used to control the plant layout, analysis of outdoor wind environment and indoor ventilation with butterfly, determine the location and the size of the building vents. Therefore, the digital model is used to simulate the structure deformation and the stress, determine the structure thickness of the ice shell. Export model data, draw architectural drawings, determine the internal design. The visual effect of Rhino models is used to evaluate the artistic effect of the buildings. In aspect of construction, the digital model is used to control the processing of inflatable membrane, set positioning, and air press control. And through 3D scanning, the digital model of the construction mode and the ice shell was generated, which is compared with the digital model to determine the safety of the structure. This is the architectural effect after the project was finished. It expressed the logical of material and the structure. It has formed an artistic effect of order and power. This is the picture of construction process and the details texture of the ice shell. The building group. The picture of indoor space effect. The elements such as materials, structure, ventilation, hole, and has become the elements of architectural indoor space artistic elements. Part of the indoor space. This is a picture of the actual use in the building. Project opened on December 22 and closed on January 26 because of the COVID-19. It operated for 34 days. There are no structural or indoor environmental problems in this period. The ice shell is good climate adaptability. The internal space environment is stable, which has a good protecting for the internal ice structure. When it was removed on March 23, the outdoor temperature reached 10 degrees above zero. The project was reported by Discover of UK and CCTV of China. This year, our team further explored the combination of ice shell structure and the traditional ice structure. We designed and constructed the project named Ice Dreamland. The total construction area is more than 1,800 square meters. This is the Harbin Ice and Snow World this year. Because of the COVID-19, it has closed. The construction process photo, 1, 2, 3, 4. The 30 meters ice shell was all located on the ice masonry structure. 6 small ice shells with span of 6 meters are supported on 3 sides by ice walls. Internal of main hall. Internal of main hall, a hole is opened in the middle of the shell. It's for lighting, ventilation, and looking for the top of the main tower of the park, just like this picture. The landing part of the middle shell divides the space. At the same time, it becomes the visual core of the internal space. According to the different space location and the size, we designed the stage, bar, dining, and other space. The effect of small room. In addition, this year we also designed the ice pavilion project on the square by Songhua River. Only 5 points supported the 12-meter ice shell. Through the research, design, and the construction practice of ice shell architecture, we have the following opinions. Ice and snow architecture is a part of nature and a common work of human and nature. Ice and snow architecture design should adhere to the design with nature, adapt to the nature environment, apply the principle of nature, create the beauty of nature. The original beauty of structure is an expression of nature beauty in architectural projects. Digital design methods and tools are important to support the realize better understanding of nature, better conforming to nature, and better cooperate with nature. Find the wisdom of the code region, establish smart design, construction, operation, and maintenance. Integrating system based on digital twin is the future of ice and snow architecture. Of course, there are still many questions to be answered in ice and snow architecture. We look forward to communicating and cooperate with you, and welcome to Harbin the next winter. Thank you very much.
Great. I think it's a fantastic talk, especially on the snow and ice structure, which Professor Luo Peng successfully implemented and invited, not only designed by his own team, but also host a lot of global teams go to Harbin to present this kind of very special process, how to design and construct the snow ice structure in a very short time. A lot of question goes to Luo Peng, I think, because ice and snow is really interesting. Very interestingly, have their very special material performance. We can see the form is generated by the software, especially based on different kind of Rhino plugin tools. And also we can find in the process, the scaffolding is really special to make the formation more interestingly. And most of the success project is by some pneumatic structures system. I think also I can imagine a lot of special technology, how to folding and unfolding this kind of pneumatic structure to find the supporting scaffolding system for the ice structure. And Virginia here, you also make research on the pneumatic structure. Probably you can set up a connection to Mr. Luo. I think that is also should based on different kind of plugin for this kind of scaffolding system for the ice and snow structure. And secondly, I think it's interestingly because the weather, the climate, year by year in the winter is a very special opportunity to construct this kind of experimental structure in a very short time. But at the same time, I'm quite curious on the crash down process for the structure, because the temperature will totally change in the whole winter, especially after the snowstorm. I think the snow load goes to extremely buffer loading to the structure. And have you ever tested this kind of buffer loading extremely strict condition for this kind of structure? Meanwhile, it's really interesting in the winter to spring time. I think after melting of this kind of structure, what kind of performance could be occur in the process, and also have a lot of value to make research for this kind of snow and ice shell structure. And thirdly, I think as to the working flow, a lot of plugin is not just Rhino Vault. You talk about Caramba, Abacus. I think it's quite a combination of embracing this kind of all software play their important roles in the process, and also the collaboration between architects and structural engineer. Mr. Luo mentioned is also very important as well. I think a lot of questions, but I think as a scenario of the research, the ice shell could be a very interesting topic year by year to improve this kind of instrument-based design methodology. But I think lastly, I think the question goes to what's the limitation of this kind of instruments? Because the formation tools by the Rhino Vault or by this kind of plugin will have their limitation for the stylistic form of shell structure. So what's the next for the ice structure should be a great challenge. I'm looking forward for more solution and more talk with you. Thanks a lot for this fantastic lecture. And the next, we would like to invite Ms. Cao Ting. Dr. Cao Ting is a postdoctoral researcher in the chair of structural design at ETH Zurich, as well as a guest researcher at Aalto University, Southeast University, and Beijing Jiaotong University. She has education background and practical experience both in architecture and structural engineering. Her research mainly focuses on the design-oriented approaches to the integration of architecture and structure. Specific research areas include design application of 2D, 3D graphic statics and the freeform surface structure in architecture, the smooth polyhyper surface structures. Her presentation today will focus on the compositional order of structure. Let's welcome Ms. Cao Ting. Would you like to share your screen right now?
Yes, thank you, Professor Yuan. I can share my screen now. Wait a few minutes, 2 seconds. What? Sorry, wait a few seconds. Sorry. Yes, I'm a researcher in a structural design research group at architectural department. We have a universal method in our chair. We use it to teach structural design to students in the architectural department. And we also use it to do the research questions of ourselves. But the most important thing of this universal method, that's graphic statics, is that it can support a new design thinking of architectural design. In the presentation, in this short presentation today, I will try to compact the design thinking, this new design thinking into this abstract compositional order. Here, before we go to the detail of this presentation, of this topic, I would like to first discuss about discuss one question: what's the meaning of structure in a general sense? Generally speaking, when we talk about the structure, like a structure of a book, we normally talk to the relations between different chapters. This is how the author, they can organize the content of different chapters into a good story. Then if we're talking about the music, we are talking about the relation between different notes. Because one note cannot make a music, only a group of notes and the relation between they can make a good melody. And also, if we're talking about the structure of a family, actually we are talking about the relation between different families. So generally speaking, structure is an arrangement and organization of interrelated elements in a material object or in a system. So in this sense, I would say structure actually is a certain abstract relationship between different objects. So if we are going back to our research fields, we are generally talking about load-bearing structures. For the load-bearing structure, we normally talk it or think it as a predefined shape or typology. That something is already existing and you cannot change it too much, like the beams, columns, truss, or arch. Something has a solid experience. We never think about what could be the abstract relations behind this structure typology, and or how can we change these relations, and how can our design could benefit from this change. So if we don't consider the structure as a predefined shape, we should find a universal way to describe all the structures. The fundamental meaning of the structure is to transmit loads to the ground. So the transmission of the loads of the forces in the material will become force flows. Force flows, we also call it as form diagram in graphic statics. If we want to find out the right shape of the force flow, we must ensure all the loads in the force flow is in equilibrium, like these loads here. I mean, a load is where the forces intersect with each other. And yes, one thing we need to pay attention is like force flow, in this case, is a relation between nodes in equilibrium. So it represents an abstract equilibrium relation. It's not the actual shape of the structure. By manipulating the loads in equilibrium, like change the number of the loads, the position of the loads, and the collectivity between the loads, we could get thousands of variations. Each variation could represent a new equilibrium relationship in structure and a new load path to transmit forces to the ground. So force flow, it can deform and grow according to the same principle. That's the principle of equilibrium. Here, we discuss the first layer of meaning of force flow as a relation, as the equilibrium relation in structure. However, since it's abstract and operative, we could also define it as a certain compositional relation in architectural design. Such as in this example, this is a building designed by a concept. It's an auto-plat office building. I mean, the architectural intention by the concept is to lift up the ground floor of this building, so they could have an open space at the ground floor of the building, which responds to the public space of auto-plats. In this case, they have to achieve this big span. Then they may use the whole total height of the facade as the structural height of this huge beam. If we check the force flow inside, actually it looks like a normal V-truss. However, this V-truss-like force flow here doesn't represent the actual shape of the structure. It represents a compositional order of the solid walls and windows in the facade. So in this case, I will say here, the force flow or the structure represent a relation between elements within an object. Here is the same, it's a similar situation. In this Russia pavilion designed by Ogiati, he wants to achieve a kind of curtain, a soft curtain, a sense of soft curtain in the facade. But if you check carefully, we will find arrangement of this curtain element are also defined by the equilibrium relation, the structure equilibrium relation lying behind. This is where the structural logic and architectural concept can merge together. This is an example designed by Kong. This is a Dhaka hospital. Here, from the first glance, you may think the reversed arch doesn't make sense structurally. This is because you judge the structure according to the appearance. Because the typology of the arch tells you arch can only stand in this way, not the reversed one here. However, if you don't judge the structure according to their predefined shape, according to their appearance, but understand what's the logic lying behind, like how the forces are actually transmitted in an arch, you will understand why the arch here and the reversed arch could get equilibrium with each other. So this could get a small conclusion. It's like we shouldn't judge the structure according to the appearance, but for the logic lying behind. That's how we could create something new for our design. Yeah, here I will say like the relation represented by the force flow can go beyond one object. Like in this case, the Horizon Innovative Center designed by Carrots. Yes. This is in this case, the equilibrium of the force flows define the compositional order of all the elements in this spatial system. Here, you may see the variation of the columns is different one from other, but all these variations are coming from the same simple equilibrium principle, which is this one. The two inclined columns could balance with each other through the slab. Starting from this simple equilibrium relation, we can manipulate the points, the loads in equilibrium, and then we can get more variation of the columns in space. Then in this case, we change the geometry, then we have to re-achieve the equilibrium relation. That means we need to introduce horizontal force in the slab. This horizontal force in the slab will be transmitted to the facade and will bring down to the support by the element in the facade. So here it means like in this building, the order to arrange the inclined letters in the facades are defined by the equilibrium relation lying behind. So I would say in this case, force flows become a relation between elements in a system. Here is a similar situation in a beam wall system. Beam wall is a special structure element because it works. It looks like a wall, but it works like a beam. So if you just judge the structure according to the experience, you will think it's just a traditional load-bearing wall because it looks exactly the same as a normal load-bearing wall. So in this sense, you will assume that all the walls should be placed in the same position on each floor. However, this repeatedness and regularity in the normal load-bearing walls is the one what Christian Carrots want to break up in the first strat apartment. He or his engineer knows very well how the walls and the slabs could work together to create the global equilibrium. Here, if we look from architectural appearance, we will think these walls are placed randomly and irregularly. However, all this the variation of the walls combination could all started from a simplest equilibrium relation. That is, the wall supported symmetrically by two points, and the cantilever parts are balanced with each other through the walls inside or the slabs above and below. By changing the points in equilibrium, we could get a lot of variations in the combination of walls. However, this will also raise the question of equilibrium. So in this case, the wall is activated again. We have additional horizontal force the slab is activated again. Yeah, we have additional forces in the slab. So when we place all these walls together, we should make sure the additional horizontal forces in the slab can be balanced with each other. So at the end, we can achieve the global equilibrium. The global equilibrium is the equilibrium relation also decides a relation between elements in a system. Yeah, here we talk about different relations in architecture and structure. Some of them are more close to the load-bearing function of the structure, or some of them are more close to the definition of architectural space and appearance. However, I would, in this case, conclude all of them as an abstract compositional order, because all these relations are discussing about elements and relations between elements. No matter the element is abstract one or it's a material object. Here, there would be one diagram could represent all these relations. That's force flow. Force flow is an abstract and operative diagram. With this diagram, as what we described before, we could generate a lot of variations. Then here will come to another question. It's like, since we have a lot of variations, that's a good advantage for us, but how can we decide which one is the best choice for design? Then in this case, we have to think about from two sides. From the structural side, we normally judge the shape of the force flow according to the performance of structure, which would be the most efficient load path to transmit the load to the ground, because the force flow actually is the path to transmit loads to the ground. And architecturally, we will judge force flow according to the visual perception and the spatial experience in the architecture. That means the force flow, which kind of force flow, when they respond to a spatial relation for the architectural element, and which kind of combination of this element could result in the best visual perception and spatial experience. In this way, force flow as an abstract diagram, they could merge the performance thinking in structure and the perception requirement in architecture into one. So in this case, I would say force flow could work as a mediator between architectural and structural design. Here in our own design, we try to use force flow as this mediate, this geometric operative mediate, to emerge the architectural requirement and the structural logic in our design. This is the competition we did last year for a Sky Street design in Nanjing. I mean, in this design, the first question we need to solve is a big span. It's around 60 meters between these two buildings. So our design first starts from a normal truss-like force flow. This force flow doesn't suggest the real shape of the structure, but it suggests a relation, equilibrium relation, and also for the compositional order to arrange these walls in space, because this force flow will somehow define the side walls in the center corridor. Here we add more horizontal slab. In this sense, we could create more equilibrium nodes. By manipulating these nodes, we can get more variations on the force flow. When we change the force flow, we also change the order to place this element. I mean, in our design, we try to create different visual and spatial experience in the corridor of each floor. So that's why we started a 3D formation of the force flow, which also leads to the change of the corridor walls in different floors. Then the next step questions comes is like, how are we going to define the side walls? The side walls are cantilevered from the central structure. Here we always place the side structure symmetrically on two sides. So the two cantilever parts could balance with each other through the tension or compression in the slab. Yes, and this is the way how we can achieve the global equilibrium of the structure. At the end, yeah, I mean, this is the position of the walls and the slabs, and the guidelines lying behind it. Yeah, at the end, when we look at the building from an architectural point of view, the walls things are arranged randomly and irregularly. However, the structural logic lying behind is very simple and regular. This structural regularity, the difference between the structural regularity and the architectural readiness is what we want to achieve according to this project. And this is also, we think, could make this project interesting. So this is a test for what I described all before, how to make use of force diagram as a compositional order to control the equilibrium relation and the compositional relation in architectural design. I mean, for sure, this one, since the force flow is a graphic, operative, and abstract diagram, it's made mainly from points and vectors. For sure, it's very easily to be digitalized, to be applied as a digital tool to help us develop design. And in our group, there are already someone developing some tools in this way. Yeah, they mainly judge the development of this tool according to the performance. But what I want to stress in our presentation is like the perception, which is more related to the architectural design, is also very important for this design thinking. Okay, that's all. That's my presentation. Thank you.
Fantastic. I think Cao Ting gave us a profound insight into the graphic statics based equilibrium thinking on the global or abstract essential of the structure in architecture. That is totally a kind of style from ETH. I think in the past few years, we have a lot of collaboration with a lot of professors there, including Philip Block. I think this kind of very fundamental thinking can give a very strong perception or give us very special possibilities actually in the very abstract ways for the future of contemporary architecture potential possibilities. The transformation of this kind of force flow is actually very, I think could not be visualized without the tools. I think the instrumental tools developed by this kind of like Cao Ting, the PhD or postdoctoral researchers, and gave very interesting benefits to the knowledge in architecture in the future, because this kind of visualization is a kind of a design thinking process, which based on the digital development and give us a bright future that is totally can change the structure system and totally can set up the linkage from the past of the knowledge, like 2D graphic statics to 3D or multi-dimensional graphic statics that is based on this kind of computational design tools. I think that's a profound insight into the essential part of the structure in architecture. That is fantastic. I think probably we should set up some further discussion in the future, and that can give us more interesting on the essential how to thinking in this kind of very fundamental or the common ground understanding of the forces, how this kind of flow of forces could be translate or make some transformation in the design process. So thanks a lot to Cao Ting. So last but not least, we have another speaker today, whose name is Xiang. Xiang is a postdoctoral researcher in Tongji, and great congratulations to him. He just got an assistant professor title in Tongji University. So in the past 2 to 3 years, he actually working with me, working in my team, and gave his a lot of contribution in our research projects. And Xiang used to be, got his undergraduate in Tongji University and coming to Tongji, and then got his PhD from University of Darmstadt. And his research especially focused on the structure performance-based design, and after working with me, transferred to this kind of robotic fabrication methodology, integration of how to implement the structure performance methodology into the robotic fabrication and construction process for the project. So tonight he will give us a special speech. The topic is structural innovation in the area of digital materiality. So please, Wang Xiang.
Okay, thank you, President Philippe, and hello everyone. It's a great honor of mine to be here to learn from other guests about their fantastic work, and also to share with you about some of my researches. As it has been introduced by Professor Philippe, I have joined the team I have joined the Professor Philippe Yuan's team since 2017 and just finished my postdoc job, and then will work as an assistant professor in the Digital Design and Research Center in the College of Architecture and Urban Planning in Tongji University. So my research is focused mostly on the innovative structural design and the robotic fabrication technique for such structures. So when I'm thinking of this topic of today, I don't know whether my idea or the structure I have created, whether the structure is recessive or explicit. So, but there is definitely a very strong thing in my idea, which is dominated by the material. So I think I want to talk mostly in this kind of direction. I think rather than to go very deep in the structural theory and to think about how to do the calculation with new method, but the thing I'm interested in is to think how we can use new materials or to create new system of structures to help the materials to work better, and then also what we can learn from the old building technique and transfer that with the new advanced technique. Like if you have watched the last 3 weeks ago, you will know that the secret from the Princeton University, they have used 2 robots to build this kind of masonry and brick structures and automatedly. And also how we can learn from the Asian builders and to find the intelligence in their thinking of structures, and then how we can transfer that or use the recent advanced computational technique and to make some innovations. So today I want to share with you some of my research in the project. So I think the sequence will also from the time sequence. The first thing is that what I have done in my PhD period, then I have created or make some researches on a kind of structure, and that is special for the thin materials. And we created that, and we named that as the cellular cavity thin shell structure. So the left picture is from the book, the IL series from the Phytols Institute. This is a kind of a bacteria in the water. And we will see the nature form of structures is not like how we usually design, like in the steel structures and the orthogonal structures. And the right thing is what I have built in for my PhD studies as demonstrators. They have a little similarities to each other. And the idea is how we have these ideas, because my supervisor at that time, they have a research funding, which is mainly about how we can build with the papers. So he asked me whether it is possible for me to try to develop a system that we can build shells with thin paper, this kind of material. So I think it's very interesting. At that time, the idea is mainly nature-inspired or bio-inspired solutions. So we think about the cells, how they combine our skins or some other structures. So maybe the original idea is very simple. If we can build a shell with a lot of cells and then build every cell with these papers, and everything is fine. So that is what we have built for at that time. The structure is a dome with a diameter of 5 meters, and they are built by 180 cells with the materials of 1 millimeter pressed paperboard. So they have several membranes and will be hollowed inside. And then even the structure is very lightweighted, but it shows a great stability. So if you can see a person who is about 60 to 70 kilograms, he climb up the structure, it shows also great stability. So as a full-scale structure. So the our hypothesis is something like this. So if we consider about the shell structures, it can be defined as a curved surface. Then, and if we want to build the structure as a lot of cells, then it will be a tessellation problem, and how we can tessellate the whole shell space. And if we consider different cells as some mass point, then we can just draw these blue lines, how the forces can be transferred from the adjacent cells. And if this kind of blue force system or the fields can be in the equilibrium state, then the global behavior of the shell can be found. This is for the form finding process. But because we are using very thin materials, there is another problem. It's not the global ones, but the local ones, which is the buckling problem. Like if we press a very thin box, the structure will be suddenly have a very large curvature and then collapse. So my research at that time is to set up this kind of system, how we can get this kind of cellular cavity structures. And it's considered about the tessellation, and then consider about the geometry details, mainly with a target to build everything with developable surface. And then we need to consider about the local behavior and of the structure and how we can choose the appropriate forms. And we also did some deep researches of the materials with some tests to get the materials parameters for our analysis. And then to the local problem, because every cell will be ideally under axial compression, then we have actually 3 kind of a basic possible selection of the shape of the skins due to the definition of developable surface, which is the conical ones and the fold one and planar ones. Then we have done some buckling tests with the FEM software, and we also did some real test, physical test with the DIC technique to see the buckling behavior of the different variations. Like this is when this is under actual compression, we can see how it behaves and how the structure buckles when it comes to the critical load. And after that, I also have set up the method how we can define the geometry and how we can define the construction details or sequence of the whole structures. And we test that for many times during my PhD time. And then it comes to how to understand the structure behavior for this kind of system. Because for our hypothesis is very simple, but actually there is no materials along the road where the force flows. So because it's hollow for every cell. So actually, when we understand the structure, it's very complicated. It's a coupled system of one system of these kind of circumferential ribs, and then another system is the covering membranes with 2 sides. And then we have tested the different analysis with models and with different load cases to know how this kind of structure behaves really. And the final solution can be shown by like this picture. If the structure is mainly under its self-weight, we can see that the whole load will be mostly taken by the covering membranes. And for this kind of ribs, it takes very few loads and almost doesn't work. But if the whole structure is under a dynamic load case, like the wind load, this kind of supporting ribs will suddenly provide a lot of stiffness for the whole structures. And then that is how their jobs for the whole structures. And it's very, and another thing is that the smaller the cell you have and the deeper the cone you design, then the structure can be better. And it's very interestingly, we have built the shell in the 2015 in the expo of IAS in Amsterdam. And after 1 year, we have seen another pavilion which has been built by the Innsbruck University in Vienna. They have testified our idea from another way. You can see they have also used this kind of conical surface and in a very deep way. And they use thinner materials, also paper 0.75 millimeter. And in this case, you can see there is no circumferential ribs, only the membranes, it will take structure. And then after my PhD in 2017, I have been invited to come back to Tongji to take a group in the DigitalFUTURES 2017. We have built a very free-formed, purely free-form structure with also almost 200 cells. But this is a pure free-form one. And to testify the whole design process, whether it works in this case. So after that, I want to share with you another series, which is for another typology of a structure, which is about bridges. It's actually the later jobs is I have done is mostly in collaboration with and also under the guidance of Professor Philip Yuan. So it's kind of our team's work. Because I have joined the team in 2017, so the bridge projects I have collaborated and contributed in is mostly in the two bridges in 2018 and 19. So this is the 2018 bridge where we are testing a new construction technique of 3D printing. Is called, it can be simply called as 3D metal printing, but the name is wire arc additive manufacturing. And it's something like this. A gun is welding the metal layer by layer, like the FDM technique in 3D printing with plastic. So we have tested that firstly from some prototype with chairs. This is a student's design of the chair, and to use some combination of linear elements like the trusses for a solid shape, and then let it work as a chair. And then we want to move that into a bridge. So because the bridge, the basic form is very hard to change. It's like an arch system. So we want to make it a combination of arch and trusses. So then that is how we get the basic idea. And then is the basic form finding of the shape with two catenary lines. And then to use the 3D topology optimization method to firstly optimize the whole design domain of the shape. And then we calculated the possible principal stress lines for this optimized domain, and then extract the control lines. And then we also need to consider about the stairs. So with this all system, we finally chosen the method of the which is the ground structure method in the 3D topology optimization. And the idea is like we provide firstly as many as possible combinations of the the bars where it can be placed. And then we use the finite element method to evaluate the structure performance of the system, and then reduce the bars which works which doesn't work, and then finally we will have optimize the shape. And this is the before the final post regionalization of the optimization, and the right one is after the regionalization as what the form we have chosen. And then finally we use the robot arm to print everything automatically, and we cut the structure into 7 parts, and here we have a steel frame to help us to control the basic form, and then let the robot arm to finish everything. So this is what we have finally for the bridge. It's very lightweighted, and we have lots of people working on that to test whether our idea just works. And then in 2019, we have finished another bridge, which is we call the multi-materials robotic fabrication, and with 3D metal printing and fiber winding. And the idea why we have this bridge or this form is rethinking of the way we chosen to define the form for this kind of building techniques, because we are using 3D printing, but the form we have chosen in last bridge is still the linear form. So from this aspect, we want to make some new progress, whether it can the thing can show the concept of 3D printing. So we have tried to print this kind of flower-like or tree-like structures, and we applied the 3D topology optimization method also firstly for the chair design. This is a girl's design for a chair, and then she printed everything and finished the chair by herself to test this workflow and concept. And then finally, you can see the whole structure for the bridge. We divided that into 2 parts. The purely structure can be a very lightweighted skeleton-like structure with 3D printed 3D metal printing technique. And then the stairs and the sidewalks, they are finished by the robotic winding of the carbon fibers and the glass fibers. And for the glass fiber and carbon fiber things, we also use the idea to think about structure behavior. And we firstly calculated also the principal stress lines of the surfaces under its load case. And then we want to arrange our fibers more along this direction of the direction the force flows. And then this is how we generated the winding sequence of the robot path planning. And then this is finally how the robot wind the whole structure. And then this is finally what it looks like. And also another very lightweight structure, but it's showing our idea and our attitude of how we should design the structure with our building techniques. And this is from the bottom side, you can see the structure. And then from the front side, you can see the sidewalk and the stairs. And then the last one is also a series, which is about shell structures and its building technique. And rather than the pure form finding techniques, I also care a lot about the efficient building technology for the shell structures. So the idea is like this. So we think the shells is very efficient. We can use very few materials to have a very long span. But when we consider about the fabrication process, you can see especially when the form is very complicated, a lot of materials or the cost will be used in the formwork system and for the fabrication. They are almost wasted after the shell is built. So with this idea, and I have worked or helped Professor Philip Yuan in our collaboration with the ETH team by the Professor Philip Block. And at that time, we want to we want to make a combination research where we can use also form finding technique for shells and also use our advanced technology, fabrication technology of 3D printing. So our idea is like we can just print some planar panels and then bend that into a shape, and then the bending will store a lot of the energy into the structure, and then will provide enough stability for the whole structure. If we can, for example, we can pull some concrete or put some bricks on top of that, then it can be a very efficient formwork system. So at that time, we have tried to generate a design to fabrication system, how to deal with this kind of a concept. And we also deal with the problem, how to simulate the large deformation process in the bending process, and how to define our final shape of the system. And then how to 3D print that and to plan the passes for the robots. And then finally, we can just build the structure or the formwork by simply put the things on site on the right position and then connect the different joints, and then the structure will bend itself. And if it is bent, and we can put some bricks, the first layer brick on top of that, then when it's hardened, and we can put another layers of the bricks on top of that, then finally the shell will be built. And with this method, we have built this experimental pavilion as a demonstrator with 3 layers and almost 50 millimeter cross sections or thickness, and a very large span shell. And we also tested with other examples to make this kind of bending active formwork for concrete, for us to pull the concrete and make it stable. And we also think that into for maybe bridge designs, like we think of this corrugated bending active formwork with 3D printed technique, and then we can pull concrete on top of that, then it will become a structure. And we also designed the design working flow for this kind of a concept. And we have tried that into also a full-scale bridge design in our studio with the MIT team. And this is finally how the formwork is built. It's also very lightweighted, and then we put the concrete on top of that and make it a very stable bridge. And it also stands today across this pond. And finally, after we have so many demonstrators about this idea, we finally got a chance, and with Professor Philip Yuan's team, which is in collaboration with Mr. Zhang's team and the Zhun project. At that time, we have built this kind of a compressive formed brick shell, which has the longest span of 40.5 meters with the cross section with a thickness of 170 millimeter. Also 3 layers of bricks. At that time, the idea is that maybe we can use a modular system of 3D printed blocks and make it together with the PU as the insulation. So we can make the formwork also work together as part of the architecture itself. Then if we can design it correctly, then the whole structures can be divided into maybe, in this case, is more than 1,000 blocks of these 3D printed blocks. And for the pattern design, we'll also make some new changes. We designed that firstly as a reciprocal structure, but we have, instead of the normal method of reciprocal structures with this rotation method, we have chosen another reference and use a new reciprocal form, which is called the next array to be used in our structures. There are two advantages, which the first is that when it goes to a local point where the curvature of the geometry is very high, then the eccentricity of the different bricks will be lowered. And then the second one, the forces or our patterns will be better adjusted to the direction the force flows. And then with this idea, we have built a whole formwork system. This is the building or the construction assembly process. We have different holes on the adjacent walls of different cells or bricks. Then what we need to do on site is just to put it in the right position and then use screws to connect the adjacent modulars, and then everything will be fine. So this is documentation of how we build this shell. It's finished by within two months. Also very not only very quick, but we have very low waste of materials. And this is what the interior looks like after the supporting steel frames is removed, and with a very complicated form of structure. Then we collaborate with also Mr. Zhang's team to calculate the formwork's stiffness or stability. And the right picture is by Mr. Zhang's team. So you can see if the structure is designed in the right form, it can take a lot of load, maybe extremely high load. And we also consider about the dynamic behavior of the structure to simulate different kind of earthquake mode for the structure. And we also tested that on site to put 90 tons of sandbags according to the mode the earthquake will go on the structure, and to test whether the structure is safe if it's under some possible earthquakes. And during the tests, we also tested the displacement of the structure in different test points. We calculate the real displacement and compare that to the finite element results, and then testify that finally. And also we have this opportunity when we have a tour of the architecture journal in China. They have organized this event, and we have so many people finally go as a live load on the structure to test the safety of the structure. Then that is what we have as the final shape of the shell as an architecture. And here's what you can see under the biggest leg of the structure. You can see the formwork also stand on under the pure structure as part of the architecture. So this is all of my presentation, and thank you very much.
Thank you so much to Wang Xiang. I think it's a really fruitful lecture sequence tonight. Already time up, but I think still it's a great opportunity for all of us. If you want to put forward any questions, would be welcome. And also Antonio or Virginia, if you have any questions, you're also welcome to put forward to all our guests today. I think we have a lot of very talented young generation in China, especially want to introduce them to the world. I think DigitalFuture World is a special platform to link the global researchers and from different regions. And last week, for example, we invited some expertise from Russia. So this week we invited specialists from China. But I think it's a great platform for this kind of such kind of communication. So we can see not only the new possibility of what is digital futures in the world, but also we have a lot scenarios which happen globally in different regions. So a lot of questions for me actually, but I think New Leach is coming. Welcome.
Thanks.
Do you have any
questions?
Yeah.
Can I ask a question? I was intrigued by the structures in Harbin, the ice structures. And I wonder, my question really is what happens, because ice expands, right, when it gets colder. And what are the particular structural challenges of working with ice when it starts to melt? I mean, I can imagine it's a very different properties to working with masonry or something. I just thought it was very intriguing working with ice, but there must be some very special problems about melting that cause problems. Maybe not. Maybe as it melts, the structure gets a certain strength.
Yes. Mr. Luo, would you like to give some feedback to Professor New Leach?
Okay, thank you for the questions. I think the material is important to the ice and the snow architecture. So we use the paper and mixed with the ice together to enhance the material. On the other hand, the environment is also important. The temperature is very important to not only the structure, but also the construction. But in Harbin, it's very cold in winter, and the winter is a long time. So we have the opportunity to make the ice shell. Okay, thank you very much. And welcome to Harbin, maybe in the future, next winter.
Thank you.
Okay, thank you.
So Marina put forward a question to Xiang. Would you like to answer the question in the talks? Xiang.
I would have to look at the questions. So the last work, the wooden shell. I think maybe the questions is asked about the relationship between the different works, and I think for our research or thinking of the how we do research is mainly on the reflective way of our thinking. We always ask questions to the thing we have done and think what we can do later. So you can see, and in only this idea to use 3D printing in the formwork for shells, we have different solutions like the bending active structures, and also pure simple bending or the coupled bending technique for different forms. And then finally, for this big structure, we also think of the way to use a packed structure, and like a reciprocal one with discrete elements to think of this. So these are all kind of testing the possibilities. I don't know whether it's like a priori, but it's based on some experience of us, and then to think whether there are some other solutions. So I think in the later, maybe we have already something which is not very good in the wooden project. Like we want to use formwork without waste, but finally we still need to have some temporarily steel frameworks as some support for the formwork structure. So we are also thinking how to reduce these ones, like to make it as a pure self-supporting formwork, or consider about the assembly process for that. So I think all the diagrams and the process of the materialization is how to modify our thinkings and how to think other new solutions for the structures. And maybe if we have new idea, we need to think of how we can set up a system, not only for the form finding, for the generation of the geometry, but also need to think how we need to, how we can build the structures with the pure materials. So, so they are always be reflected by ourselves. This is a very, very always in a changing process, and that is how I think of these questions.
Yeah, good. I think from my perspective, I'm quite interested in the research of Liu Yan, although he is a historian, but I think he actually in the past few years, from his book and from his papers, I find it quite interesting. He put forward a question about reciprocal, like this kind of chopstick bridge. He made research in the past few years, gave a profound knowledge system. He put forward a question and make some comparison, not only in the Renaissance time in Europe, in Novation in Japan, and he finds in some area of China, this kind of reciprocal timber structure actually very developed in ancient time of China. And also he questioned why this kind of truss structure never happened in China. So I'm very interested in that from a historical perspective, to make research in this kind of structure-based research. So Professor Mr. Liu Yan, would you like to give us some analysis on this kind of your research on the historical background? And would you like to address what's your research, and after you listen to all the guests today put forward their lectures, would you like to make some comments on that?
Thank you, Professor Yuan. Thank you for your comments on my research and also the questions. Well, today I'm mainly come here to study because actually the structural design and how nowadays architects could put forward this advantage technology in create the artworks of structure in so many new ways that is totally, almost entirely something new. I really got my knowledge exploded today. So it's really, I got a great inspired from all these speakers. Thank you all very much. Well, about the question, actually, I'm not really sure because, yeah, architecture historians really focus totally different aspects of architecture. I would say myself more like a historian rather than an architect study. So our study focus sometimes on the anthropological aspects and archaeological aspects. But I think there's something I really got from some new ideas, some new inspirations I got from the speakers. During my research, sometimes I was criticized by the architects or by some common people. So they would ask, what is your research going to benefit the modern design or going to benefit our life today? And I would say that I hold an attitude against the imitation just on the form, on the structural form, but which had been could we say hold market for maybe the past decades, the past century. So when people talk about what is architecture history going to be used from Liang Zicheng's time and even until the very beginning of this century, that people mostly thinking about how we can learn the form from the ancient buildings. But today I learned from many speakers, for example, the ICE, Dr. Luo Peng's ICE structure, and I forgot the other one, but talking about the grass structure that inspired the modern engineers, not only imitating the form, but how that ancient people deal with the material and how they deal with the atmosphere of the space, and how, to think about from construction and other aspects. I think this is quite inspiring and also quite encouraging to me. So since I myself, it is also expressed in my talk that I'm some kind of against the idea that we imitate from the structural form, the very superficial aspects. But I think, yes, today we can, when we talk about what we can learn from the ancient world or from the tradition, from all other cultures, there's many more aspects, and that aspect could be work together to develop.
Okay, great. I think it's really interesting. We, on the one hand, we want to learning from the history, from the tradition, because structure not only as a kind of form, but also kind of like a signal which can signify different kind of contents from the structures, maybe not purely structure, but actually goes to different kind of narrative analyzed in the history from this kind of tradition form. So that is really interesting part of the structure as a form. At the same time, I want to go to the other hand, like Ms. Chao Ting put forward this kind of very global or very abstract scenarios or research. I think that is totally focused on the graphic statics. That is very purely the essential part of structure design. That is, I think, the two sides is like the two sides of coins. One is goes to the very symbolic form, structure as a symbolic form, and on the other hand, structure is purely contemporary elements in design process. I think that is probably the most interesting part, because Chao Ting put forward the concept as composite order, compositional order, and Mr. Zhang name is a composite structure system. So Ms. Chao Ting, would you like to make some comparison about the compositional order and this kind of composite structure system? Do you want to say something on your understanding of what is Mr. Zhang's doing, very composite solution in the practical scenarios, and your research in ETH is purely, I think, from an essential part of structure performance-based design. Would you like to say something on that?
Thank you, Professor Yuan. I think that's a very interesting question. You should ask Mr. Zhang first. Yes, as myself understanding, here the compositional order I mentioned here is an abstract relation. I mean, this relation could be interpreted in different levels, in a structure meaning and also in an architectural meaning. And that's why I said this could be, I mean, this compositional order, this relation could become a mediate between architecture and structural design, because we are always talking about this integration between architecture and structure, but we never talk about like exactly what can we do. I mean, graphic statics, yes, it has an advantage because it's a graphic method and it can analyze and design structure. But in my opinion, it's like graphic statics can do something more than that, because it can basically shape the way how we think to design our architecture logically, not the structure, but the architecture logically. And for the presentation of Mr. Zhang, I think, I guess maybe the composition, what he mentioned in his project, is more from fabrication and fabrication point. I guess, I'm not so sure. you could ask him later. But I want to stress out is like stress that here that in my case, this is abstract conception. It's not something related to the component of a structure or component in a fabrication or component of architecture or component of structure. Yeah, it's something more abstract. Okay.
Zhang, would you like to say something on this topic, the question I put forward?
I think a pure concept is important, and I think such as the but in our work, I need to think how to build them out, and so many things. It's not that pure. In fact, I don't think I want to composite all things or complex things is better. At very beginning, I like pure things, but when we going, we'll find I have to do something. But when we composite them, I don't just think about okay, this way can fix everything. That's okay. I want to composite in another logic. That logic is composite with different clues or different thinking. By this way, we can show a structure. It's complicated or composite, but it's also beauty or something else. And what the something else is can be everything. Maybe some history or some culture, that all can be something close for me. That's what I think when you design something or composite them.
Thank you. I think recessive structure we put for the topic today is really profound. And from the fruitful talks from all the speakers today, I think it's a different kind of perspective, not only from the historical research, but also from the structural engineer perspective. And also, most importantly, I think is from the real scenarios in the real practical process, how we can implement this kind of structure knowledge to present them in architecture design process. So structure is really essential knowledge of architecture in the whole history, because gravity is always there. So not only, no matter how the technology develop, but we never change our attitude to fighting with the gravity of the Earth. So it's a permanent, interesting topic. And afterwards, we would like to organize a special writings on this topic, and would like to invite all the speakers today to give your papers on your practice and on your very specific research. I think we want to make more deep or insight discussion from this kind of presence, absence of structure logic in architecture. And also we want to make further discussion in the new tools or new instruments, how to develop new tools can give us a kind of a human-machine collaborative process to give more potential creativity of the future in architecture. So that is a lot topic. Probably right now the time is not enough for the further discussion, but I think we want to keep forward on this topic, and to to set up more interesting people to invite them into this kind of community to make further discussion on that. So right now, the online presentation is really meaningful. Thanks for your contribution, your time, and your great research to show us on the DigitalFuture platform, which rather than the offline lectures, this is more quick and more efficient ways to set up a learning platform, global learning platform, Newlich and me, we would like to set up in the future. And based on that, we have a lot of international PhD courses or the different university courses could set up the credits on this platform. So thanks for your contribution, and all if you agree, I want to put all your talks on both YouTube and Bilibili. I think it's a great opportunity to make some promotion for you guys, the Chinese young generation, and present your works to the world. So thanks a lot for your engagement, and thanks a lot for your time. And Neil, would you like to say something to ending today's talk?
No, I just simply say that I think this is, I think there've been a lot of very positive comments in the chat. I think people have been very impressed by the work that's been shown, and it's great for people around the world to see what's going on in China. And I think there's some very interesting work happening. I would like to congratulate all the people presenting. It was a really interesting, I just see some of the comments, mind-blowing. So it was mind-blowing. Thank you very much indeed. Thank you.
Thank you. Thank you to all of you. Bye-bye. 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 See you next week. Bye-bye.
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 Bye-bye. Thank you. Thank you, Professor Yuan. And thank you.
Bye-bye. Thank you.
Bye-bye.
Thank you, everyone.
Bye-bye. See you later. Bye-bye.
Thank you. Bye.
Bye-bye.